Good morning, John. So probably you have heard that for a long time the amount of energy entering the Earth's atmosphere and the amount leaving the Earth's atmosphere was about the same. And that was good, because if those two numbers are not equal, then we're either getting colder every year or we're getting hotter every year. But now it looks like there is in fact more energy coming in than going out. And that results in basically three things. First, more heat, which is what we call like individual molecules moving faster, which is wild. Like when you are hot, it is because the molecules that make up your body are jiggling more. Doesn't seem real, but it is. Second, you have more severe weather, which is when a lot of molecules together move around more. And because of those two, you have number three, which is probably the worst of them. Things are different. That doesn't sound so bad, except that we have built a tremendous amount of our human infrastructure designed based on the idea that things will be roughly the same now as they were in the past with regards to rainfall and temperature and stuff like that. When that stuff changes, crops might have dramatically lower yields, resulting in very hungry people. People might use their air conditioners way more than in the past, so entire power grids fail. Or forests that grew in areas that once had shorter dry seasons might burn up in fires. So that's bad, and always the first thing you should ask when something bad is happening is, why is that happening? Well, you know how when you go outside wearing a black t-shirt, you get hotter faster than if you're wearing a white t-shirt? That's because things only look black if they absorb all of the visible light that is hitting them. If the light was not being absorbed, it would either be reflected as white light or as a mirror, or it would be clear, which would be a strange choice for a shirt. So if you're wearing a white shirt, the visible light isn't being absorbed, it's being reflected, and that's why you're less hot. Absorb, reflect, or let pass through, that's basically the only three things that a material can do with light. And if the light is being absorbed, that means the energy of the light hit the molecule in such a way that it's creating movement in the molecule. The light no longer exists. The energy is now movement. And that movement can be transferred to other molecules, just like a cue ball hitting a pool ball. There are basically two ways a molecule can heat up, and we just talked about both of them. The first is that a photon travels through space and then gets absorbed by a molecule and speeds up that molecule. That's heat from radiation. And the second way is that a particle that's jiggling a lot hits a particle that's jiggling less and transfers its heat to that other molecule. When that happens in a solid, we call it conduction. When it happens in a fluid, we call it convection. So like when you're in the shade, 99% of the heat you are feeling is from convection. It's molecules in the air running into you and transferring their heat to you. But when you're in the sun, it's a mix of both the radiation and the convection, which is why it's hotter in the sun. Now, different molecules absorb different wavelengths of light. Like this book cover is mostly absorbing everything but yellow, and this one is mostly absorbing everything but red, and the red and the yellow are being reflected back. And this can also happen with gases. There can be green gases and yellow gases and brown gases. But the two molecules of interest here, carbon dioxide and methane, they don't absorb any light in the visible spectrum, which means that they are clear. We can't see them. One of the problems with methane, actually, if your house is filling up with it, you need to make sure that you know that that's happening, but you can't see it. But at certain infrared wavelengths, which the sun creates a lot of, they are black. And when we put more of them in the atmosphere, our atmosphere is a little less clear in those wavelengths, and it's a little more black. Those molecules absorb photons, they start to move around faster, they knock into other molecules, which also start to move around faster. They push on each other more and more until they have lower pressure, and that hot air starts to rise. Cooler, denser air rushes in to take its place, and that's weather now. Those hot air molecules might remove more moisture from the soil, resulting in more wildfires. They might evaporate more water from the ocean, resulting in bigger storms. We know that this happens, we know how this happens, we know why this happens, and we know what the effects are. And we know that the only way to stop it is for there to be less CO2 and methane in the atmosphere. But that is a very hard thing to do. It's very hard and expensive to remove those things from the atmosphere. It's very hard and very expensive to replace the agriculture and energy and transportation infrastructure that results in the release of those gases. It is not an easy problem to solve, but we have a very strong grip on what the problem is. And I think people can solve basically any problem if only we can agree that it exists. John, I'll see you on Tuesday.